So in our example 5, we're going the opposite direction from taking partial derivatives. This time we're given a partial derivative, and we're asked to figure out what the original function could be that have produced that. So essentially what we're going to do is we're going to integrate with respect to x. So I'm going to integrate is equal to the integral, you can think of it this way, as e to the xt cosine t dx. But now that means we're integrating with respect to x, so t is a constant. It's just like when we took the derivative with respect to x, we held t as constant. And so that means that cosine of t is just a big constant, which means you can pull it out of the integral. So cosine of t, whoops, not equals, we're going to pull that out of the integral, e to the xt dx. Now we're going to be integrating that with respect to x. Let me just remind you, for example, e to the 4x dx would be 1/4 e to the 4x plus a constant. That's going back to the old calculus 1 technique of substitution. So if that looks foreign to you, maybe check back the calculus 1 lectures here on Educator.com. It's doing a little substitution. U equals 4x and du is equal to 4 dx. And then doing that little substitution ends up with 1/4 e to the 4x. So here, we've got cosine of t. Now, you want to think about this as e to the tx, where t is a constant. So it's kind of behaving like the 4 here. So instead of 1/4 e to the 4x, I get 1 over t times e to the tx. It's just like the 4 was before. Now we have this t. Plus, now, be careful here. I want to say plus c, but remember, I'm integrating with respect to x, which means that I'm thinking of all t's as being constants. So what I'm going to say is plus any function of t. Because if I took the derivative of that, if I took u sub x of that, it would just go back to 0. So I could really have any function of t here that I like. So let me collect my terms and simplify that. 1 over t times e to the tx times cosine of t, plus I'm going to say any function of t. So this could be any function of t. This is my u of xt. Any function of t could be your c of t here. And the reason I can put any function of t in there, cosine t, e to the t, natural log of t, t squared, is because if I took the x derivative, it would just cancel away to 0. So that's my most general form for my u of xt. If you took the derivative, the x derivative, you'd get back to what we started with. And you might ask, well, where's the constant here? You can think of the constant as being built into the function of t. So this includes any possible constant that you would care to add on there. So let me recap how we figured that out. Basically, we're doing the integral, but we're doing the integral with respect to x. And so that means that I can think of cosine t as being a constant, and I can pull it out of the integral. And then I'm integrating e to the, well, think of it as e to the tx. But remember, t is a constant. So the integral of e to the tx is just 1 over t times e to the tx. Still have that cosine t. And normally I would tack on an arbitrary constant here. But since I'm doing the opposite of a partial derivative, I can tack on any function of t, because any function of t would be treated as a constant when you take the partial derivative. So this would be treated as a constant when taking the derivative with respect to x, when finding u sub x. So any function of t could be included there, and so I'm just going to include that arbitrary function of t, c of t, instead of including an arbitrary constant. And I can think of an arbitrary constant being built into it. So my final answer there is what I got from the integral plus any arbitrary function of t. And the reason that works is because if you took the x derivative, that c of t would just completely drop out, and we'd get back to that e to the xt cosine t that we started with. So that wraps up our review of partial derivatives. We'll be all set to go now for learning about partial differential equations starting in the next few lectures. If this wasn't enough review of partial derivatives, if you're still feeling a little rocky, a little bit rusty when you're taking partial derivatives, then we have a whole set of lectures on multivariable calculus, and you'll get more practice from taking partial derivatives in those lectures. So you could go back and watch those lectures again, the ones on multivariable calculus, and you'll get lots of practice with partial derivatives. This was just meant to be kind of a quick review, get a little practice brushing the rust off, so that when we start doing partial differential equations in the next lecture, you'll be ready to go. So that's the end of our lecture on reviewing partial derivatives. And I want to remind you that you are watching the Differential Equations lecture series here on Educator.com. My name is Will Murray, and I very much appreciate your watching. Take care.